So welcome back, students. So we are in the final unit of our transducers and engineering, and in this unit we are going to have we have been introduced to several different kinds of transducers in the different levels such as resistance, inductance and capacitance. So apart from this, there are several different kinds of transducers in the field. So in that few transducers that are commonly used, we are going to see in the unit number 5, and I will give a short description and a brief note over the sensors. So what are the sensors that we are going to cover in the unit number 5? I will give a glimpse over that and then we will go into the details. The first one is the ultrasonic transducer. The second one is the magnetostrictive transducer. The third one is a Hall effect transducer. The fourth one is the fiber optic transducer. Fifth one is the MEMS based sensors. And the sixth one is the bio and nano based sensors. Okay, so all these things, the ultrasonic, magnetostrictive, Hall effect, fiber optics, MEMS, bio and nano based sensors are some very special type of sensors that we will be seeing. And I have mixed one more, that is the photoelectric transducers. So we will see these 8 different kinds of sensors in 2 sessions. We will see now the first session that covers the ultrasonic transducers, magnetostrictive transducers, Hall effect transducers and the fiber optic transducers. First, we start with the ultrasonic transducers. As I have already given in the previous note about the ultrasonic transducers works in the acoustic frequency range of above 20 kilohertz. Okay, it works in the acoustic range of 20 kilohertz and it's mostly used in the proximity or obstacle detection and in level measurement, all other kinds of applications where there is going to be an obstacle present in the area. So the ultrasonic transducer has always a piezoelectric crystal which converts the electrical energy to the acoustic energy or the ultrasonic wave, or in the reverse manner, it is the ultrasonic energy, the acoustic energy is converted to the electrical signal. Usually it consists of a receiver and a transmitter part, a transmitter and a receiver section. Either it can be separate or else the same crystal can act as a transmitter and also a receiver. Now let us consider for the easy reference as the transmitter and separately the receiver. The transmitter, it produces the ultrasonic waves. The receiver receive it. Okay, here we have our obstacle. The transmitter is the one where we give in the voltage and that is converted to ultrasonic signal. It comes and hits the obstacle and then it returns back, and in the receiving section it is the inverse piezoelectric effect where the ultrasonic signal or the wave is converted to the electrical voltage. So depending upon the nearness of the obstacle, we will get the proportional output. So depending upon this ultrasonic sensor, we can construct many different kinds of applications. One is the obstacle detection. The next one is a level detection of liquids. Etc. So these are some many different kinds of applications that are possible using ultrasonic transducers. The next one comes with magnetostrictive transducers. The magnetostrictive principle explains about the property of magnetostriction. Okay, we know the property of piezoelectricity, where when a mechanical stress is applied to a crystal, it is converted to electrical energy. Here it is, when a mechanical stress is applied, the magnetic field of the material changes. Okay, and this kind of an effect is found in ferromagnetic materials. All the magnetic materials has a ferromagnetic property, so it is found in these ferromagnetic materials, for example iron, nickel, cobalt, etc. Okay, and what happens in this magnetostrictive material is that you have an, see here, we have an core of this magnetostrictive material, and over that a magnetic flux production line is wound, which acts like an electromagnet. Okay, and when there is going to be a magnetic property wound is produced over the magnetostrictive material, then there will be a force that is produced. This red color line, what I am indicating is the force that is produced. Okay, so there is a conductive material and the magnetostrictive ferromagnetic material over which there is an coil wound, and when we are going to give in or change the magnetic flux, okay, then there is going to be a force or a magnetostrictive force that is produced, or a change of magnetic mechanical stress is induced in the material. Okay, so this magnetic force or the stress which is induced is represented as displacement. The same thing can be done in the opposite manner. When you are going to give a magnetic stress over the material, then there will be a change in the magnetic permeability. Okay, this effect of the inverse magnetostriction is called as Villari effect. It is the inverse of magnetostriction. Okay, so again I repeat about the magnetostrictive property. The magnetostrictive property is found in ferromagnetic materials such as iron, nickel and cobalt. Okay, and here what happens is that when you are giving in a magnetic permeability or a magnetic flux over a material, then the material exerts a real stress or a mechanical stress is induced in the material. That's what you see here, and this kind of a property can be used for production of displacement. Okay, and the inverse, when you are going to give a stress over to the material, then there will be a change in magnetic flux. Okay, and this is called as Villari effect, and this is called as inverse magnetostriction. Okay, this kind of properties can be utilized in many different kinds of application where there is going to be a change in magnetic field over there. Okay, so this is about the magnetostrictive transducers. This is used in bottling plants when there is going to be a ferromagnetic material or the thing. We can use the direct method for detection, and for the displacement production we can go in for the magnetic property. The third one comes in the Hall effect transducer. Okay, welcome back. Again we are now going to see about the Hall effect transducer. First let us look into what is Hall effect. Okay, let us think about a current carrying conductor. Okay, this is a current carrying conductor. which is connected in this fashion, and it also consists of a magnetic flux perpendicular to the current. Then there occurs an EMF perpendicular to both, to the other side of the current carrying conductor, and this EMF that is generated is called as Hall voltage. Okay, this is called as the Hall voltage, which is proportional to the current and also to the Weber of magnetic flux. Okay, so this is the Hall effect property. When in a current carrying conductor which consists of a magnetic field which is going through the conductor, then there will be a voltage induced which is perpendicular to both this current and also the magnetic flux. Okay, and we get the output, and this is proportional to the amount of current carrying there and also to the magnetic flux. So this is the typical Hall voltage which is produced, and it is a passive element because we are giving in an external supply. So here by changing the current value or else on the flux value, we will be able to adjust the Hall voltage. Okay, so this property is exploited in many different kinds of applications. Something like when you are going to have a magnet, you remove the magnetic field and you are going to give in an external magnetic field to the sensor, then it will be able to detect the magnetic field present in that region by the production of Hall voltage. Okay, so that is a many major application. Imagine any kind of a situation where there is going to be an induced magnetic field and the sensor will be able to detect the magnetic field. This is again applied in many different kinds of metal oriented applications where there is going to be a attraction or a production of magnetic field. Again a bottling plant. It should be a conductive medium of electricity. Okay, so this is the Hall effect transducer. Next comes the fiber optic sensor. As we all know about the fiber optic sensor, you might have studied in your previous classes. The fiber optic sensor works on the principle of a reflection, one of the major effects of light. So what are the other major effects of light? They are the reflection, refraction, diffraction, interference, all other many other properties are there. And reflection is a very major property of light here, which is we are going to exploit in a fiber optic cable. First we will see the anatomy of a fiber optic cable. This is a core of a cable, and over the core is a transparent region which is solid. Okay, and it is in a lengthwise it is present, and over the core there is a coating that is called as the cladding. So this has a refractive index of mu1 and this has a refractive index of mu2. Okay, and we are passing in light through a light source. Let us think it is an LED, and we have a photodetector present over here. What is a photodetector? It may be an LDR, photodiode, or a phototransistor, or a photomultiplier, etc. Okay, so we are giving in a photo source which is an LED, and then light enters here. As the refractive index of both are very different, it has a higher refractive index. The cladding has a higher this is the core, this is the cladding. The core has a lower refractive index compared to that of the cladding, and it goes like this. There should be no light refracted out of the core. Everything should get reflected, and we should get the, in ideal condition, whatever the intensity that is given in should come out. Okay, that is the ideal condition when there is no disturbance there in the fiber optic cable. Okay, but it won't happen like that in many cases when there is going to be a disturbance. And this property of traveling inside without any loss of signal is called as total internal reflection. Okay, it is a property of total internal reflection. If you see here, to explain in detail, I can just draw a, if this is a mirror or a glass, okay, this is a ray and this is a reflected ray. Usually there will be a refracted ray over here, okay, and this is the loss, what is happening. Okay, this is the reflection angle and this is the refraction angle, and depending upon that we will have a loss over what is happening, and we want to entirely send back all the reflected light to the back region and no refraction should happen. Okay, so this is what happens inside a fiber optic cable, and what we are giving in lumens, which is mentioned in lumens, the amount of light should be appearing here in the photodetector and we should get. Here the voltage is given and it is converted to a light, and here we are getting in the light and we are going to convert it into voltage. Okay, so this is the basic principle of a fiber optic cable. Okay, now how we are going to convert this fiber optic cable into a sensor? Just I will tell you an example for force. Now let us imagine this is a 1 meter long, okay, and we are getting in the entire signal outside. We are applying a force of 5 newtons to this fiber optic cable. What will happen immediately? This is the cable without any problem, and then there will be a curvature happening over here because of the force applied. Okay, then this reflection, the intensity of the received side will be low. It will be different or it will decrease. This decrement in the voltage is proportional to the amount of force that is applied to the fiber optic cable. Okay, this is the main property of the fiber optic sensor, where we are going to measure the force or pressure. This difference in the voltage or the reduction in the voltage is proportional to the force or pressure. The next construction for temperature. Now imagine this is your core and this is bent over here. It is bent over here. You have a polymeric material with a metal coating. With a metal coating. Okay. When that is put up in a constant temperature, the light which is passing in will come out. Okay. But when there is going to be a temperature difference, temperature increment when it happens, this temperature will hit the metal and then it will change the polymeric property which is present here. This is the polymer, which will affect the bending polarization. So light which is going in will get, the polarization will be diffracted differently and there will be a reduction in voltage. So this reduction in voltage will be proportional to the temperature and we will be able to measure the temperature. So we are able to now convert a fiber optic cable into a force measurement or a pressure measurement or a temperature measuring device. Okay. We are again back to transducers engineering. We are in the unit number 5 and we are left with just 3 topics of MEMS and then our photoelectric transducer, bio and nano sensors. First we will start with the photoelectric transducer, which you are very much used up. Just recall back your previous experience in fiber optic sensors. We have been introduced to the photoelectric transducers in the manner such as it is an active transducer which converts voltage or light energy to voltage. A solar cell is an example. A solar cell is an example of an active photoelectric transducer. This is an active photoelectric transducer, and if you want passive examples, we have our LDR, light dependent resistor, photodiode, phototransistor, and finally our photo multiplier. All these things convert the incident light to again electrical energy. So hence these are photoelectric transducers which convert light to electric energy, and these are passive elements. This needs external source, but this is an active element which is a solar cell or a photovoltaic cell. This don't need any kind of external source. It directly converts the light incident over it into electrical energy. So a cumulative amount of different solar photovoltaic cell produces your entire solar panel where we get our voltage. The next is the most important state of art property of the sensors, which is the MEMS, which is micro electro mechanical systems. These micro electromechanical systems based upon the property of all your photolithographic techniques. You have to remember all your things what you have read in your unit number 1 and linear integrated circuits. The photolithography, miniaturization. Miniaturization is the prime aim of a micro electromechanical system which integrates electrical and mechanical systems in the micrometer level. For this we use different kinds of techniques such as photolithography, wet and dry etching, sputtering, etc. All these things are this miniaturizing techniques. Okay, I will explain a single thing in detail about the MEMS, which will cover the bio and nano sensor and also the MEMS based sensor. Okay, now imagine a cantilever beam. Imagine a cantilever beam which is of dimensions 10 micrometer in length. Okay, and you need to fix strain gauges at different positions. Then if it is 10 micrometers, will be only 2 micrometers of this strain gauges to measure the stress and strain of this cantilever beam. Okay, so this type of a cantilever beam which is of 10 micrometer length and a breadth of only in nanometers, I can say, can be done only using a micro electromechanical technique of photolithography of wet or dry etching techniques. So it is now we are having all our strain gauges and it will be connected to a Wheatstone's bridge circuit and we will get our output. So this can be applied anywhere wherever we want to get the output. This is used in microfluidics. Again, this is a micro based fluidics system. Now I will convert this kind of a small cantilever beam output to a bio or a nano sensor to detect tuberculosis. Now again I will draw the sensor here. Okay, I will draw the sensor here. It is again 10 micrometers. Okay, this sensor or a cantilever beam, how we are going to convert this cantilever beam into a biosensor, we will see. Every disease consists of a pathogen. So we are going to take TB, which is tuberculosis, which is produced by Mycobacterium tuberculosis, and it produces a disease causing agent called as antigen. And for this antigen, our body, WBC or the white blood cell, produces the antibody. This antibody produced by our white blood cell is specific to the disease. Okay, it is very specific to the disease, and this antibody is taken or it is specially manufactured outside artificially and it is coated over to this cantilever beam. And these are called as receptors. Now, after coating the cantilever beam, which is of 10 micrometer thickness, with your antibody of Mycobacterium tuberculosis, you can nullify your, we have strain gauges here and there over the cantilever beam. You can nullify this strain gauges cantilever beam to zero condition by normal methods. Okay. Then you expose this cantilever beam to your sputum or blood, which is infected with the Mycobacterium tuberculosis. If it is infected with TB or tuberculosis, then the antigen will come and lock with this receptor. Okay, these are all in molecular level. This is also a molecule, this is also a molecule, this antibody is a molecule and antigen is also a molecule. This come and attaches with the antibody because it gets attracted. Then the molecular weight of the cantilever beam becomes different and the zero condition is disturbed. Okay, otherwise if it is not present, it won't come and attach and the zero condition won't be disturbed. Okay, so hence we will be able to identify whether the exposed blood is infected with Mycobacterium tuberculosis or the person is infected with tuberculosis, and we will be able to say whether this is right or wrong. Okay, so like this we will be able to, now we have converted a cantilever beam mechanism in a bio or a nano scale for the detection of Mycobacterium tuberculosis, which is responsible for tuberculosis. Like this, kits are available and we are having sensors in the present day state of art technology. So like this, we have started in our first unit with error detection, accuracy, precision and all these things, and finally we have come out to the state of art technology of nano and biosensors. I hope you have enjoyed your course very much, and I expect your comments in all kinds of levels. Thank you very much.